Just as flowing water in a river constitutes a water current, moving charged particles constitute an electric current. During lightning, charges flow from the clouds to the earth. This flow of charges is not steady but momentary. Charges accumulate on the metal body of a car while it is moving. When you touch this car with bare feet, you experience a mild shock. This is because these charges get short-circuited through your body and reach the earth. These are examples of a very short duration or momentary electric current. In most of the devices that we use, there is a steady flow of charge. For example, in the working of an electric torch, a steady current passes through the circuit of the torch to make it glow. Let us conduct a simple virtual activity to understand the concept of electric current. In a closed space, a large number of positive and negative particles move around randomly. Divide the space into two parts using a vertical plane surface through which the charges cannot cross over. Cut a rectangular-shaped window in the vertical surface. Now, the charged particles can move from the left side of the partition space to the right side and vice versa through the window opening in the vertical plane surface. Let us now formulate a sign convention for the motion of the charged particles. The left to right motion of any charged particle is taken as the forward direction of motion, which is taken as positive. The right to left motion of any charged particle is taken as the backward direction of motion, which is taken as negative. In time t, which is equal to 10 seconds, let us assume that the number of positive charged particles crossing over from left to right is equal to A, which is equal to plus 100. The number of positive charged particles crossing over from right to left is equal to B, which is equal to minus 20. The net positive charge movement is equal to A plus B is equal to C, which is equal to plus 80. The number of negative charged particles crossing over from left to right is equal to D, which is equal to plus 40. The number of negative charged particles crossing over from right to left is equal to E, which is equal to minus 10. The net negative charge movement is equal to D plus E is equal to F, which is equal to plus 30. The net charge movement Q is equal to C minus F, which is equal to 50. A steady electric current I is denoted by Q by T. By substituting the values of Q and T, we get the value of I as 5 units. A steady current is positive when it moves in the forward direction, that is, from left to right, and negative when it moves in the backward direction, that is, from right to left. Instantaneous current at any time t is expressed as IT is equal to limit t tending to 0 delta Q by delta T, where IT is the current at time t. Delta Q is the net charge flowing across a cross-section during the time interval delta t. that is, between time t and t plus delta t. The SI unit of current is ampere and is represented by A. In the virtual activity that we just went through, we observed a random motion of the charged particles within an enclosed space. During the random motion, the charged particles not only collide with each other, but also with the wall of the enclosed space. After collision, they get deflected and move again randomly with the same velocity with which they collide. When an electric field is applied to the enclosed space, the random motion of the charged particles is changed to unidirectional flow that constitutes an electric current. This experiment can be conducted in the ionosphere layer of the atmosphere, where there are charged particles moving randomly. If an electric field is applied to a small space in this layer, the same motion of the charged particles can be observed. What are these moving charged particles that constitute an electric current? In individual atoms and molecules, the negatively charged electrons and positively charged nuclei are bound to each other and therefore are not free to move independently. Bulk matter is made up of a very large number of atoms and molecules, which are so closely packed that the electrons are no longer attached to individual nuclei. There are some materials whose electrons are totally bound to their nuclei and can't be separated even on applying an electric field. These materials are called non-conductors or insulators. In metals, some electrons are practically free to move within the bulk material. These electrons are called free electrons. When an electric field is applied across metallic objects, an electric current develops in them due to the unidirectional flow of these free electrons. Therefore, metals are called conductors. Electrolytic solutions are also categorized as conductors, as both positive and negative charges move when an electric field is applied. In this chapter, we will emphasize on solid metal conductors, where a current is constituted by the movement of negatively charged free electrons in the background of fixed positive ions. Consider a metal object when no electric field is present. Electrons in the object will be moving randomly and colliding with the fixed ions. An electron, after colliding with an ion, gets deflected with the same velocity with which it collides. The direction of velocity of the electron after collision is completely random. There is no preferential direction for the velocities of the electrons. On average, the number of electrons traveling in any particular direction will be equal to the number of electrons traveling in the opposite direction. Therefore, there is no net electric current. Let's apply an electric field to the metal and see what happens to the motion of these electrons. To observe the motion of electrons very clearly, let us use a conductor in the shape of a cylinder of radius r. We take two thin circular discs made of a dielectric material of the same radius r as that of the cylinder. There are q number of positive charges distributed across one of the discs and q number of negative charges distributed across the other disc. These two discs are attached to the two flat surfaces of the cylinder, creating an electric field which is directed from the positively charged disc to the negatively charged disc. The electrons are accelerated and move towards the positive charge. On reaching the positive charge, they neutralize the charges on the disc. The unidirectional motion of these electrons constitutes an electric current. This electric current exists only for a very short time, that is, till the charges are neutralized. We can attach the two ends of a battery or a cell to the two discs to maintain a steady electric field and thereby obtain a steady current. Ohm's law states that V is proportional to I, where V is the potential difference across the conductor and I is the current flowing through the conductor. Let this be equation 1. To replace the proportionality sign by equality, we introduce a constant and write equation 1 as V is equal to Ri, where R is the constant of proportionality and is called the electrical resistance of the conductor. Let this be equation 2. The SI unit of resistance is ohm. The resistance R of a conductor depends on the composition of the conducting material and the dimensions of the conductor. To understand how the dimensions of a conductor affect its resistance, let us conduct two simple activities. Let's take two identical conductors of length L and cross-sectional area A. Place them side by side such that their ends touch each other, so that the length of the combination is 2L. The current I flowing through this combination is the same as that flowing through the individual conductors. The potential difference V across the ends of each conductor should be the same as they are identical and the same current I is flowing through them. The potential difference across the ends of the combination of the two conductors is 2V. The resistance of each conductor is expressed as R is equal to V by I. The resistance of the combination of conductors is represented by RC. RC can be calculated by applying the above formula for the combination. Substituting V by I is equal to R in the above equation, we get RC is equal to 2R. From this activity, we can conclude that resistance R is directly proportional to the length L of the conductor. Let this be equation 1. Coming to activity 2. Let us divide the conductor into two by cutting it lengthwise so that it can be considered as a combination of two identical conductors of length L, but each having a cross-sectional area of A by 2. The potential difference applied across the two conductors is V. If I is the current through the combination of the conductors, then the current flowing through each conductor is I by 2. Then the resistance of each conductor is obtained as equal to 2R. From this activity, we can conclude that having the area of cross-section of a conductor doubles its resistance. Generalizing, we can write resistance R of a conductor is inversely proportional to its cross-sectional area A. Let this be equation 2. Combining equations 1 and 2, we can write resistance R is proportional to L by A. Let this be equation 3. Replacing the proportionality sign with equality, we can write equation 3 as R is equal to rho into L by A. Let this be equation 4, where rho is the constant of proportionality which depends on the material of the conductor and is called resistivity. Substituting equation 4 in Ohm's law, we get V is equal to I into rho into L by A. Let this be equation 5. Current per unit area is called current density, J. Current density J is expressed as I by A, where area A is normal to the direction of the current I passing through the conductor. Let this be equation 6. The SI unit of current density, J, is ampere per meter square. When E is the magnitude of the uniform electric field in the conductor of length L, then the potential difference V across the conductor is expressed as V is equal to EL. Let this be equation 7. Substituting equations 6 and 7 in 5, we have EL is equal to the product of J, rho and L. On simplifying the above equation, we get E is equal to J into rho. Let this be equation 8. The above equation can be written as J is equal to E into 1 by rho. Substituting 1 by rho is equal to sigma in the above equation, we get J is equal to E into sigma, where sigma is the conductivity of the conductor. This equation is the equivalent form of Ohm's law. An electrolytic cell is a device which maintains a steady electric current in an electric circuit. Let us now understand the construction and working of an electrolytic cell. An electrolytic cell consists of two electrodes, positive P and negative N, immersed in an electrolytic solution, also called an electrolyte. The electrodes, when dipped in the electrolyte, exchange charges with the electrolyte. Due to the exchange of charges, the positive electrode P acquires a potential difference Vp between itself and the electrolyte solution immediately adjacent to it. The magnitude of Vp is always greater than 0. Due to the exchange of charges, the negative electrode N acquires a negative potential Vn relative to the electrolyte adjacent to it. The magnitude of Vn is equal to or greater than 0. When there is no current, the potential throughout the electrolyte is the same. Let us now understand the concept of the electromotive force of an electrolytic cell. The potential difference, V, between P and N is Vp minus of minus Vn. which is equal to Vp plus Vn. Let this be equation 1. The voltage or electric potential difference across the terminals of a cell when no current is drawn from it is its EMF. Thus, E is equal to Vp plus Vn, which is greater than 0. Let this be equation 2. EMF is the short form of electromotive force. E actually represents potential difference, but was called electromotive force by the scientist who first used it, and the name continues to date. So far, we have studied the components in a cell and how potential difference comes into existence. Let us now connect the two electrodes of the cell to the two ends of a resistor to understand how a cell actually functions when it is connected in a circuit. A resistor with a resistance equal to R is connected across the cell. A current I is established from C to D. As a steady current is maintained, the same current I passes from P to N in the external circuit and from N to P within the electrolyte present inside the cell. As the current passes through the electrolyte, it must have a finite resistance R, which is known as the internal resistance of the cell. To clearly understand the difference between potential difference and EMF, let us replace the resistor R in the circuit with a resistor of infinite resistance. We can now write I is equal to V divided by R equal to 0. Here, V is the potential difference between P and N measured across the resistor. From equations 1 and 2, V, the potential difference between P and N measured across the electrolyte, is written as V is equal to E. Let this be equation 3. From equation 3, we can conclude that EMF, E, is the potential difference between the positive and negative electrodes in an open circuit. That is, when there is no current passing through the cell. Let us now return to the original circuit consisting of a resistor with a finite resistance. Let us now connect the two electrodes of the cell to the two ends of a resistor to understand how a cell actually functions when it is connected in a circuit. A resistor with a resistance equal to R is connected across the cell. A current I is established from C to D. As a steady current is maintained, the same current I passes from P to N in the external circuit and from N to P within the electrolyte present inside the cell. As the current passes through the electrolyte, it must have a finite resistance R, which is known as the internal resistance of the cell. To clearly understand the difference between potential difference and EMF, let us replace the resistor R in the circuit with a resistor of infinite resistance. We can now write I is equal to V divided by R equal to 0. Here, V is the potential difference between P and N measured across the resistor. From equations 1 and 2, V, the potential difference between P and N measured across the electrolyte, is written as V is equal to E. Let this be equation 3. From equation 3, we can conclude that EMF, E, is the potential difference between the positive and negative electrodes in an open circuit. That is, when there is no current passing through the cell. Let us now return to the original circuit consisting of a resistor with a finite resistance. Now, as the resistance is finite, I is not equal to 0. As I is not equal to 0, I also has to pass through the electrolyte to maintain a continuous flow of charge. The electrolyte has a finite resistance R, called the internal resistance of the cell. According to convention, the current from P to N through the circuit is positive. As the current I in the electrolyte is from N to P, the current through the electrolyte is taken as negative. In this case, the potential difference V between P and N is denoted by V is equal to Vp plus Vn minus I into R. Substituting from equation 2, we can write V is equal to E minus I into R. Let this be equation 4. Applying Ohm's law to the external circuit, we have V is equal to I into R, where V is the potential difference across R. Let this be equation 5. Combining equations 4 and 5, we get I into R is equal to E minus I into R. On rearranging the terms in this equation and simplifying, we get I is equal to E divided by R plus R. The maximum current that the cell can provide is when R is equal to 0. Then we have I maximum is equal to E divided by R. To avoid permanent damage to the cell, the maximum current allowed is far less than the value calculated using this formula. Let's take a conductor AB in which a current I is flowing from A to B. The electric potential at point A is VA and at B it is VB. As the current is flowing from A to B, the voltage at A is greater than the voltage at B. The potential difference V between points A and B is expressed as V is equal to VA minus VB. Let this be equation 1. As V of A is always greater than V of B, V will always be greater than 0. Let the amount of charge flowing from point A to B be delta Q in the time interval delta t. Delta Q can be expressed as the product of I delta t. Let this be equation 2. The potential energy of the charge at the initial point A is delta QVA. The potential energy of the charge at point B is delta QVB. A change in potential energy between points A and B is expressed as delta U potential, which is equal to final potential energy minus initial potential energy, which is equal to delta Q into VB minus VA. From equation 1, we know that V is equal to VA minus VB. Therefore, VB minus VA is equal to minus V. Let this be equation 3. From equations 2 and 3, delta U potential is equal to minus I delta TV. Let this be equation 4. Since the value of delta U potential is negative, it is less than 0. The law of conservation of total energy states that the total amount of energy in an isolated system remains constant over a period of time. Applying the law of conservation of total energy between points A and B, since the potential energy of the charge is decreasing, its kinetic energy must increase. Therefore, an increase in kinetic energy K of the charges is expressed as delta K is equal to minus delta U potential. From equation 4, we can say that delta K is equal to minus of minus I delta TV. This implies that delta K is equal to I delta TV. Let this be equation 5. Since the value of delta K is positive, its value is greater than 0. If the charges move freely through the conductor, their kinetic energy should increase, and they should move with greater velocity. But we know that on an average, these charge carriers do not move with acceleration, but with a steady drift velocity. This is because the free electrons collide with the ions while in transit. Due to these collisions, the kinetic energy gained by the charges is transferred to the heavy ions. And these ions vibrate more vigorously, thereby heating up the conductor. The heat dissipated by the vibrating ions is represented by delta W. This delta W is nothing but the increase in the kinetic energy of the charged particles. Therefore, delta W is equal to delta K. From equation 5, we can say that the amount of energy dissipated is expressed as delta W is equal to I delta TV. Let this be equation 6. The energy dissipated per unit time is termed as the power dissipated and is represented by P. Therefore, we can write P is equal to delta W by delta T. Substituting the value of delta W from equation 6 in the above equation, we get P is equal to I delta TV by delta T. On further simplifying, we get P is equal to IV. Let this be equation 7. According to Ohm's law, we have V is equal to IR. On substituting the value of V from Ohm's law in equation 7, we get P is equal to I square R. Let this be equation 8. Ohm's law can be rewritten as I is equal to V by R. Substituting the value of I in equation 8, we get P is equal to V by R whole square into R. This implies that P is equal to V square by R. Let this be equation 9. P, which represents the power dissipated or lost, is also called ohmic loss in a conductor of resistance R carrying a current I. This dissipated power P is utilized to heat the filament of an electric bulb to incandescence and radiate heat and light energy. Power is supplied to this resistor by an external source such as an electric cell. Similarly, there is power loss when a current I is transmitted from the point of generation to the point of utilization through transmission cables. The distance between these 2 points is often very large. The transmission cables have a certain resistance due to which there is a huge power loss. Using equation 8, that is, P is equal to I square R, we can derive an expression to calculate the power loss due to resistance in the cables. Power loss in the cable PC is due to its resistance RC, which is expressed as PC is equal to I square RC. Let this be equation 10, where I is the current flowing through a cable. According to equation 7, P is equal to IV, where P is the power generated at source, V is the voltage generated, and I is the current flowing through the cable. Rearranging equation 7, we get I is equal to P by V. Let this be equation 11. Substituting equation 11 in 10, we get PC is equal to P by V whole square into RC. That is, PC is equal to P square by V square into RC. Let this be equation 12. This equation helps calculate the power loss PC due to the resistance RC in the transmission cable. In equation 12, we can say that the values of power P generated at source and the resistance RC of the cable are constants. Therefore, it implies that the power loss by the cable PC is inversely proportionate to the square of the voltage generated. Therefore, to minimize the power loss in transmission cables, the voltage of the power produced at the point of power generation is stepped up using a step-up transformer before it is transmitted. This very high voltage is converted to low voltage using a step-down transformer placed very near to the point of utilization of power. As you learnt earlier, there are various elements used in an electrical circuit, such as a resistor R, voltmeter V, ammeter A, and battery, which are represented here. These will help you understand the various circuits dealt with in this module. Resistors are one of the important components in a circuit. Resistors are joined together to form various types of combinations to obtain the required resistance in the following three ways. 1. Series combination. 2. Parallel combination. And 3. Mixed combination made up of both series as well as parallel combinations of resistors. We obtain a series combination of resistors by joining one of the two endpoints of a resistor to the next resistor. We can make a series combination using 2, 3, and so on up to n resistors. We obtain a parallel combination of resistors by joining one end of all the resistors and similarly joining the other end of all the resistors. A parallel combination can be made using any number of resistors. A mixed combination of resistors is obtained by connecting some resistors in series and some resistors in parallel combination and then connecting the two combinations. So far, we have seen how to build various types of combinations of resistors. Next, we will learn about equivalent resistance of any combination of resistors in a circuit. Equivalent resistance is the resistance of a single resistor that can replace the given combination of resistors in the circuit without affecting the total current in the combination and the voltage across the combination. Let us now derive equations to find the equivalent resistance of the various types of combinations of resistors. Equivalent resistance of a series combination is obtained as follows. AB and CD are two resistors with resistances R1 and R2 joined in series as shown in the circuit diagram. A voltage V is applied across points A and D by joining them to the two terminals of a battery. V is the potential difference between points A and D. The charge that leaves R1 enters R2. As current is the measure of the rate of flow of charge, the same current I must flow through R1 and R2. According to Ohm's law, V is equal to I into R, where V is the voltage across the resistor, I is the current flowing through the resistor, and R is the resistance of the resistor. Applying Ohm's law to resistor 1, the potential difference across R1 is denoted by the equation V1 is equal to I into R1. Let this be equation 1. The potential difference across R2 is denoted by the equation V2 is equal to I into R2. Let this be equation 2. The potential difference V across A and D, that is, the series combination, can be written as V is equal to V1 plus V2. Let this be equation 3. Substituting equations 1 and 2 in 3, we get V is equal to IR1 plus IR2. V is equal to I into R1 plus R2. Let this be equation 4. Equation 4 can be written in the form V is equal to I into R equivalent. Let this be equation 5. From equations 4 and 5, we can write R equivalent is equal to R1 plus R2. Let this be equation 6. From equation 6, we conclude that when two resistors R1 and R2 are connected in series, the combination has an equivalent resistance equal to R1 plus R2. When three resistors of resistances R1, R2, and R3 are connected in series, the equivalent resistance for this combination is equal to R1 plus R2 plus R3. We can extend this to a series combination of n number of resistors with resistances R1, R2, and so on up to Rn. The equivalent resistance of this combination is equal to R1 plus R2 and so on up to Rn. Now let us consider a parallel combination of resistors AB and CD with resistances R1 and R2 connected as shown to a battery of potential difference V. The equivalent resistance Req of this parallel combination is obtained as follows. The charge that flows from the source, that is the battery, splits and flows out partly through R1 and partly through R2. I is the rate of flow of charge from the source, that is the battery. I1 is the current through resistor R1, and I2 is the current through resistor R2. We can now write I is equal to I1 plus I2. Let this be equation 7. Applying Ohm's law across R1 and R2 individually, we can write V is equal to I1 into R1 and I1 is equal to V by R1. Let this be equation 8. Voltage V applied across the two resistors is the same as they are connected parallel to the same battery. Therefore, we can write V is equal to I2 R2 and I2 is equal to V by R2. Let this be equation 9. Substituting equations 8 and 9 in equation 7, we get I is equal to V by R1 plus V by R2 and I is equal to V into 1 by R1 plus 1 by R2. Let this be equation 10. Equation 10 can be rewritten in the form I is equal to V into 1 by Req. Let this be equation 11. Req is the equivalent resistance of the parallel combination of resistors. From equations 10 and 11, we can write 1 by Req is equal to 1 by R1 plus 1 by R2. Let this be equation 12. Using equation 12, we can calculate the equivalent resistance Req of the parallel combination of two resistors. Similarly, when there are n resistors connected in the parallel combination, we can write 1 by Req is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. Now let us consider a situation where some resistors are connected in series and some resistors are connected in parallel. The equivalent resistance of such a series and parallel combination is obtained as follows. In the circuit, three resistors of resistances R1, R2 and R3 respectively are connected in a mixed combination. R2 and R3 are in parallel combination. Their equivalent resistance R23EQ is calculated using equation 12. 1 by R23EQ is equal to 1 by R2 plus 1 by R3. Now, R1 and R23EQ form a series combination. Their equivalent resistance R123EQ is calculated using equation 6. R123EQ is equal to R23EQ plus R1. We can calculate the equivalent resistance of any combination of resistors using the basic equations 6 and 12.